So students, we have seen in my last class Young's modulus of elasticity, simple stresses, simple strains, and Hooke's law we have seen. So today let us start with the modulus of rigidity. So modulus of rigidity, I am abbreviating modulus of rigidity as G. So modulus of rigidity G is also equal to stress upon strain, because modulus, whether it is Young's modulus of elasticity, the plural of modulus is moduli. So there are three types of modulize. Young's modulus of elasticity abbreviated by E, modulus of rigidity abbreviated by G, and bulk modulus of elasticity abbreviated by K. So this Young's modulus of elasticity is defined as stress upon strain, and modulus of rigidity is also defined as stress. Instead of stress, there should be shear stress, and instead of strain, there is shear strain. Now, what is shear stress? What is shear strain? Now, this modulus of elasticity, yesterday I have explained you, is associated with the change in length. Now let us take an example what exactly the shear stress is. Have you do one exercise, small exercise. You pick one stone in your hand and rub that stone on plain ground surface or rough ground surface. Assume this is your stone and this is your surface, slightly rough. Now if you are rubbing this stone on this surface, the contact between the stone surface and this floor surface will be there, and stresses will be developed at the surface. These stresses we call it as shear stresses. So the ratio of shear stress upon shear strain is modulus of rigidity. So this is the difference between modulus of elasticity and modulus of rigidity. So in most of the books, you will find that modulus of rigidity is a ratio of shear stress abbreviated by tau upon shear strain abbreviated by this symbol. You can abbreviate it like this also, and you can mention here shear means shear strain, and you can mention here shear stress. So ratio of shear stress to shear strain is modulus of rigidity, and the ratio of simple stress upon strain is modulus of elasticity. Now here I am trying to explain you one simple mathematical calculation. Let us assume that a compound rod is there. Compound rod means a rod made up of two pieces of varying cross sections, or a rod has varying cross sections at different lengths. So modulus of one portion is E1, modulus of other portion is E2. Loads acting are W1, W2. The lengths of the various portions are L1, L2. I shall try to draw here how the section is. Suppose this is section. Either it is a single section or it is made up of two small sections. It hardly matters. So this is W1 and this is W2. Right? Then A1, E1. So this is area 1. Suppose this is the circular in section, so area 1. This is the portion area 2. So maybe the diameter is D1 here. Here the diameter may be D2. You can easily calculate the areas of two different sections. Then here in this equation, if you look at the final equation, right, in final equation you will observe that P into A2 into E2 upon A1 E1 plus A2 E2, or if we apply the compatibility equation W1 upon A1 E1. See, A1 is in suppose meter square, E kilonewton per meter square, so it will be kilonewton upon kilonewton. So in compatibility equation W1 upon A1 E1. Now what happens? E, that is the modulus of elasticity, as it is made up of two different metals, suppose the modulus of elasticity will also be different. So this is E1 and this is E2. Now this E, modulus of elasticity, is stress upon strain, as I have mentioned here. Now stress will be equal to load divided by area. I am trying to calculate for this first portion, divided by, this is the value of stress, divided by strain is change in length upon original length. So change in length upon original length is defined as strain. So suppose the strain, I am abbreviating in first portion as epsilon 1. So if I am doing some mathematical calculations, so this epsilon, that is the strain in first portion, will be equal to W upon A1 into E. So W upon A1 into E, W upon A1 into E. By this way, compatibility equation, we can write that if the strain in this portion is, suppose this load acting here is W1, here the load acting is W2, and W1 upon A1 even if they are made up of different materials is the strain developed in this portion. So it is quite obvious that the strain developed in second portion will also be equal to W2 upon A2 E2. In compatibility equations, if you will look at this compatibility equations, then you have to equate this both, that whatever the strains developed in portion 1 is equal to the strains developed in portion 2. So W1 upon A1 E1 equal to W2 upon A2 E2. This is the story behind this. So this is the compatibility equation. So in this way we can employ the compatibility equations and equilibrium equations. You know very well, summation of all the horizontal forces is equal to 0 if the body is in equilibrium. So you can easily apply the equations of equilibrium. So I want to share here that the equations of compatibility equation and the equations of what I can say equilibrium. So equations of compatibility and equations of equilibrium are to be employed to analyze compound bars. When we will deal with the numericals, we will see in detail. Now, there is one, as I have explained you, one more moduli. As you have seen here that modulus of elasticity, modulus of rigidity, you have seen here both the moduli. You have seen the difference between E and J. So students, the modulus, so the modulus of elasticity and modulus of rigidity, the differentiate, it is a ratio of shear stress to shear strain. It is the ratio of linear stress to linear strain. Now, one more moduli is there, that is bulk modulus of elasticity. And in bulk modulus of elasticity, this bulk modulus, the word itself will tell you that it is associated with volume. So most important question in most of the vivas interviews, it is asked that what are the moduli? Moduli is a plural name, right, in mechanics of solid or strength of materials. And what is the difference between these three? So Young's modulus is associated with length, modulus of rigidity is associated with shear, and bulk modulus is associated with the volume change. Now, if you will look at this, see this diagram, one cube is there and loads are acting on three different faces like this P. Now, this bulk modulus is again, modulus is stress upon strain. So, if bulk modulus is stress upon strain, but this time I will say which type of stress? Volumetric stress upon volumetric strain. I am abbreviating here as VOL. VOL means volumetric strain. So again stress upon strain, but it is volumetric stress upon volumetric strain. You all know very well, if a load P is acting like this, then stress, volumetric stress will be load upon area. And volumetric strain will be change in volume upon original volume. So this bulk modulus of elasticity, this volumetric stress for unit area A equal to 1, then it will be P divided by delta V by V. And this I have explained here. This negative and positive sign doesn't make any difference because this change in size indicates if the volume is decreased, sign will be negative. If volume is increased, size will be positive. So in this way, in mechanics of solid, there are three types of moduli, that is E, G and K. Now, we want to establish the relation between E, G and K. And if I want to establish a relation, suppose I am saying that your result is a function of marks means whatever the marks you are obtaining, according to that result will be reflected. So in mathematics you know that result is a function of marks, means I have to put some constant here k into m. This marks will be multiplied with that constant. It may be k to the power something, constant may be anything, and result will be obtained. The same way, the relationship between E, G and K, if we want to establish, we have to introduce one constant. This abbreviation is mu. Abbreviation is mu. MUE. So this mu stands for Poisson's ratio. This is known as Poisson's ratio. And with the help of the Poisson's ratio, we can easily calculate the relationship Poisson's ratio. With the help of this Poisson's ratio mu, we can easily develop the relationship between E, G and K. So Poisson's ratio, what is Poisson's ratio and how to define Poisson's ratio? So Poisson's ratio is defined as lateral strain upon linear strain. So Poisson's ratio is the ratio of strain only, so it is unitless parameter. Lateral strain, I have explained you that if suppose this is a rod with diameter capital D, lateral strain will be change in diameter upon original diameter, and length, linear strain means change in length upon original length. So if I want to calculate the Poisson's ratio for rod, then it is the ratio of lateral strain upon linear strain. So lateral strain upon linear strain, and lateral strain is change in diameter upon original diameter. Linear strain is change in length upon original length. So in this way, Poisson's ratio can be calculated. So students, in today's class, we have seen 3-4 aspects. One aspect we have seen the compatibility equation and equilibrium equations to analyze composite sections. We have seen bulk modulus. We have seen modulus of rigidity. We have seen Poisson's ratio. So in tomorrow's class, we will deal with the relationship between all the moduli of elasticity, and we will solve numericals. Any doubt, students?
Yes, sir.